Theo, you have flown, this is a aerodynamics and aircraft section of the commercial pilot written exam. You have flown to an airport in the mountains. Actually, we already did this one, so we'll skip this. You're flying an aircraft with an auxiliary electric fuel pump. When should this pump be used? And basically, it says in accordance with the pilot operating handbook instructions. That's a very generic answer, but yeah, I guess you would do that. Takeoffs, landings, and the pattern would be another answer, but that's not on here. Which statement is true about isogonic lines? Isogonic lines are lines of equal variation. So lines drawn across aeronautical charts to connect points having the same magnetic variation are called isogonic lines. Yeah, they're lines of equal variation, which is a magnetic variation. At a given airspeed, what effect will a decrease in air density have on lift and drag? At a given airspeed, what effect will a decrease in air density have on lift and drag? So if the air density is less, it's a decrease, yeah. So if you're climbing at a higher altitude, there's less dense air, drag will decrease and lift will decrease. So lift and drag also vary directly with the density of the air. Density is affected by several factors: pressure, temperature, humidity. At an altitude of 18,000 feet, the density of the air has 1/2 of the density of air at sea level. In order to maintain its lift at a higher altitude, an aircraft must fly at a greater true airspeed for any angle of attack. Why do some aircraft have a 0 fuel weight limitation? And this is to ensure that wings are not overstressed in flight. So the multi-engine airplane is where most pilots encounter the term 0 fuel weight for the first time. Not all multi-engine airplanes have a 0 fuel weight limitation published in their POH, but many do. 0 fuel weight is simply the maximum allowable weight of the airplane and payload, assuming there is no usable fuel on board. The actual airplane is not devoid of fuel at the time of loading, of course. This is merely a calculation that assumes it was. If a 0 fuel weight limitation is published, then all weight in excess of that figure must consist of usable fuel. The purpose of a 0 fuel weight is to limit load forces on the wing spars with heavy fuselage loads. Go to next. When does an airplane stall? The answer is when the critical angle of attack is exceeded. Next. And we'll pull up the figure, zoom in. The line for point G to point F is represented on an airspeed indicator by the yellow arc. So yeah, from 160 to 200, this is the yellow arc, this is all bolded in yellow. It starts at 160, and at F is red, so that's never exceed speed. And so yeah, that's correct, yellow arc. Simple. On a fixed pitch propeller, the angle of incidence is at its highest pitch at the hub of the propeller in order to provide uniform lift across the blade. That is true. So if you look at a propeller, you'll see the pitch angle is the sharpest, closest to the hub. And if you look at the tip of the propeller, it's a less of a pitch because that's spinning faster in the air. Wind is an important factor in avoiding wake turbulence because wingtip vortices drift with the wind and at the same speed. Wind is an important factor in avoiding wake turbulence because wingtip vortices drift with the wind and at the same speed. That's true. They do descend and spread out, if I understand, but the wind can carry them. In the event your engine should begin to overheat, you should reduce the power, enrich in the mixture, and descend. reduced power, and rich mixture and descent. The cruise propeller has increased efficiency for cruise operation and has a higher angle of attack than a climb propeller and creates more drag at cruise speed. So yeah, that's a fixed, I guess they're referring to a fixed pitch cruise propeller. It has an increased efficiency for cruise and has a higher angle of attack than a climb propeller, which is less angle of attack on each blade because it's better for climbing and it gives you more torque, and it creates more drag at cruise speed. It has a higher pitch and therefore it has more drag. More drag results in lower RPM and less horsepower capability, which decreases performance during takeoffs and climbs, but increases efficiency during cruising flight. Parasite drag increases at the square of the airspeed. Parasite drag increases at the square of the airspeed. In steady state, as airspeed decreases to near stalling speed, the total drag becomes greater. So parasite drag increases at the square of the airspeed. The most common high lift devices are flaps. That's true. When you put your flaps down, it provides a lot of lift. You are in a coordinated, constant altitude turn. An increase in bank angle will result in a load factor increase and stall speed increase. That is true. You're going to have more load factor, and your stall speed will also go up because your angle of attack is increasing. Which factor remains constant for stalls? Angle of attack. Yep, the wing will stall at the same angle of attack no matter of the airspeed. All right, go back to a figure. Point A represents, so yeah, if you look at total drag, it is the lowest point, so it's minimum drag. Zoom in. Oops. The LD ratio at a 4-degree angle of attack, which is here, is approximately the same as the LD ratio for 8.7. So we take our line, 4-degree angle of attack, we go up to this point here, and we go across to here, and go down, and I guess it's almost a 9. Yeah, it actually is 9.7. So you go up to 4, across, and down. It's almost at 10, but the closest answer choice offered is 8.7. So it's actually off, but that's the best answer, so you select that one. If an airplane is flown at LD max, lift drag ratio max, the total drag will be at a minimum. If an airplane is flown at LD max, lift drag max, the total drag will be at a minimum. While accelerating, hold on, let me mark that last one. While accelerating for takeoff, you notice the airspeed is constant and remains constant for a few seconds. This can be caused by a wind shear to an increasing tailwind. So the airplane is moving through this air, but basically it has wind coming from behind it, so the speed through that air mass is actually staying the same, so the The answer here is wind shear is dangerous to an aircraft. It can rapidly change the performance of the aircraft and disrupt the normal flight attitude. For example, a tailwind quickly changing to a headwind causes an increase in airspeed and performance. Conversely, a headwind changing to a tailwind causes a decrease in airspeed and performance. In either case, a pilot must be prepared to react immediately to these changes to maintain control of the aircraft. The turn coordinator gives information about rate and quality of turn. The turn coordinator gives information about the rate and quality of turn. An aircraft uses two types of turn indicators. The first is a turn and slip indicator, and the other is a turn coordinator. Because of the way the gyro is mounted, the turn and slip indicator shows only the rate of turn in degrees per second. The turn coordinator is mounted at an angle or canted, so it can initially show roll rate. When the roll stabilizes, it indicates rate of turn. Both instruments indicate turn direction and quality, which is coordination, and also serve as a backup source of bank information in the event an attitude indicator fails. Coordination is achieved by referring to the inclinometer, which consists of a liquid-filled curved tube with a ball inside. The performance factor of dividing total weight of an airplane in pounds by the wing area in square feet is known as wing loading. The performance factor of dividing total weight of an airplane in pounds by the wing area in square feet is known as wing loading. While completing a 30-degree bank turn, you extend landing gear and your airspeed decreases by 10 knots. What effect does this have on your rate of turn? While completing a 30-degree bank turn, you extend the landing gear and your airspeed decreases by 10 knots. What effect does this have on your rate of turn? The rate of your turn increases. So you're completing a 30-degree bank turn, you extend the landing gear and your airspeed decreases by 10 knots. So your airspeed decreases, your landing gear goes down, and that causes drag, so you decrease airspeed by 10 knots. What effect does this have on your rate of turn? So the rate of turn increases because you have to reduce your bank angle to maintain the same altitude. The rate of turn is the number of degrees of heading change that an aircraft makes. The rate of turn can be determined by making a constant of 1091, multiplying by the tangent, blah, blah, blah. Forget all that. Let's just go to the next question. Okay, refer to figure 4. If an aircraft with a gross weight of 3,000 pounds was subjected to a 60-degree bank constant altitude turn, the total load would be 6,000 pounds. If an aircraft with a gross weight of 3,000 pounds was subjected to a 60-degree constant altitude, the total would be double that. So yeah, 60-degree bank doubles the weight, so 2 Gs. So yeah, load factor by 2, 60-degree. So we go to 60 degrees up to that line, and the load factor is 2. So 2 times 3,000 is 6,000 pounds. All right, cool. Under what conditions are indicated airspeed and calibrated airspeed approximately the same? And that's at cruise and higher airspeeds. So calibrated airspeed is indicated airspeed corrected for installation error and instrument error. It is not possible to eliminate all errors throughout the airspeed operating range. At certain airspeeds and with certain flap settings, the installation instrument errors may total several knots. This error is generally greatest at low airspeeds. In the cruising and higher airspeed ranges, indicated airspeed and calibrated airspeed are approximately the same. Refer to the airspeed calibration chart to correct for possible airspeed errors. The angle of attack of an airfoil directly affects the coefficient of lift produced by the airfoil. The angle of attack of an airfoil directly affects the coefficient of lift produced by the airfoil. What effect does deploying wing spoilers have on landing an airplane? They make the wheel brakes more effective because it reduces the lift. If a pilot operates an airplane at the same airspeed at 15,000 feet and at 5,000 feet, what effect will be on lift and drag? Lift and drag will increase at 5,000 feet because there's more air. You're flying an aircraft in cold temperatures when you notice an oil temperature lower than normal. If you're flying around in cold weather and you notice oil temperature is lower than normal, what's the possible cause? It says that the wrong oil viscosity is being used for the cold temperature conditions. If the air temperature is higher than standard, the service ceiling would be lower. That makes sense because density altitude will be increased at a given altitude. You have been hired as a commercial pilot at a new employer who utilizes aircraft equipped with FADECs, FADECs. A FADEC is a system that utilizes a computer to control components of the aircraft that manipulate the engine and propeller. So a FADEC is a system that utilizes a computer to control components of the aircraft that manipulate the engine and propeller. If an airplane flies from an area of cold, dry air to an area of warm, moist air while maintaining the same airspeed, what effect will this have on lift and drag? So cold, dry air to area of warm, moist air. So because the air is warmer, it's going to have less density, so lift will decrease and also drag will decrease. Both warming an air mass and adding moisture to it have the effect of decreasing the air density. So yeah, I guess if there's moisture in the air, there's less air, so it's less dense. A benefit of a FADEC in a reciprocating aircraft engine is the mixture is automatically optimized for the flight conditions. The mixture is automatically optimized for the flight conditions. If an airplane is flown at LD max, total drag will be lower than total drag at CL max. So if an airplane is flown at the lift to drag ratio maximum, its total drag will be lower than the total drag at CL max. So the pilot can control the lift. At any time the control yoke or stick is moved forward or aft, the angle of attack is changed. When the aircraft reaches the maximum angle of attack, lift begins to diminish rapidly. This is the stalling angle of attack known as CL max, critical angle of attack. Examine the figure, noting how the CL increases until the critical angle of attack is reached. An airplane that is unstable around the lateral axis will dive and climb progressively steeper. So longitudinal stability is the quality that makes an aircraft stable about its lateral axis. Longitudinal stability is the quality that makes an aircraft stable about its lateral axis. It involves a pitching motion as the aircraft's nose moves up and down in flight. A longitudinally unstable aircraft has the tendency to dive or climb progressively into a very steep dive or climb, or even stall. So you look at the lateral axis, which is wingtip to wingtip, and that's the axis that the plane is moving on. So that means the longitudinal axis is moving up and down. So that will mean it will dive and climb progressively steeper if it's unstable. Why is stalling airspeed higher when the center of gravity is moved forward? This is caused by increased wing loading. So if you move weight forward in the airplane, you actually have to trim back to keep the nose level, and that causes increased wing loading. The aircraft stalls at a higher speed with a forward center of gravity location. This is because the stalling angle of attack is reached at a higher speed due to increased wing loading. In steady state level flight, lift will oppose the downward force of weight. In steady state level flight, the lift will oppose the downward force of weight. In steady state level flight, the lift will oppose the downward force of weight. That's correct. That's easy. All right, refer to figure 1. When steady in flight with the airspeed represented by point A, the airplane total drag will be at a minimum. That's easy. When an airplane leaves ground effect, induced drag will increase. When an airplane leaves ground effect, induced drag will increase. Longitudinal stability is measured about which axis? Longitudinal stability is measured about the lateral axis. Longitudinal stability is the quality that makes an aircraft stable about its lateral axis. It involves the pitching motion as the aircraft nose moves up and down in flight. Which statement is true regarding the forces acting on an aircraft in steady state climb? So if it's steady state climb, everything is 0. That's right. In steady flight, the sum of forces is 0, which is weight and lift and drag and thrust. There could be no unbalanced forces in steady straight flight based on Newton's third law, which states that for every action or force, there is an equal but opposite reaction or force. This is true whether flying level or when climbing or descending. While on a standard rate turn to the left, you retract the landing gear and your airspeed increases 12 knots. You're on a standard rate turn to the left. You retract the landing gear and your airspeed increases 12 knots. In order to maintain a standard rate turn, you will need to increase the angle of bank because now you have less drag. If an airplane is in a 60-degree constant bank turn, you could expect the airplane to stall at the same angle of attack as in level flight and at a higher airspeed due to an increase in load factor. That is true. It always stalls at the same angle of attack, but it can stall at a higher airspeed because you have a higher load factor. Refer to figure 2. You plan to demonstrate a steep turn and want to review the stall speed at a 45 bank angle, flaps and gear up, gear and flaps up, power on. The stall speed will be 64 knots. That's right, stall speed right here, 64, you just look right there. Your planned departure will be from an airport with a higher density altitude than what you had previously experienced. You should know that under this condition, indicated airspeed at liftoff will remain the same. So the explanation for this question: takeoff, landing, and stall speed listed in the POH are indicated airspeeds and do not normally vary with altitude or temperature. At higher elevation, at any given airspeed, the aircraft's true airspeed is higher than at a lower altitude. Ground speed is true airspeed corrected for headwind and tailwind. So at a higher altitude, given the same wind condition, the same indicated airspeed, since the true airspeed is higher, the ground speed is also higher. So there's indicated airspeed, true airspeed, and ground speed. How will lift and drag be affected when an airplane enters ground effect? Lift will increase in ground effect and induced drag will decrease. That's because the ground is interfering with the wingtip vortices, so that reduces drag. Structural damage or failure is likely to occur at above a never exceed speed. Which center of gravity position could create undesirable flight characteristics, including decreased static longitudinal stability, decreased dynamic longitudinal stability, control difficulties, violent stall characteristics, and light control pressures? And that's when the center of gravity is aft of the center of gravity envelope. So, in extreme cases, a center of gravity location that is beyond the forward limit may result in nose heaviness, making it difficult or impossible to flare for landing. Manufacturers purposely place the forward center of gravity limit as far rearward as possible to aid pilots in avoiding damage when landing. In addition to increased static and dynamic longitudinal stability, other desirable effects caused by a center of gravity location aft of the allowable range may include extreme control difficulty, violent stall characteristics, and very light control forces, which make it easy to overstress an aircraft inadvertently. So I guess aft means forward. All right, open up the figure. At which angle of attack will drag be minimum? 6 degrees. So drag is minimum at this point. Lift drag ratio. Looking at the coefficient of drag curve, okay, I guess that's CD. We can see that the CD at about 6 degrees is far less than it is at 12 degrees. 12 degrees is here. Since drag is proportional to the coefficient of drag, all other factors remaining the same, the higher the CD, the coefficient of drag, the higher the drag. Yeah, so I guess 6. You just pick the number that's the lowest. Okay. While making a standard rate left turn, you raise the landing gear and your speed increases by 12 knots. To stay coordinated, you increase your bank angle because, yes, there's left drag. What condition contributes to nose heaviness, possibly making it difficult or impossible to flare on landing? What condition contributes to nose heaviness, possibly making it difficult or impossible to flare on landing? The center of gravity forward of the CG limit. Yeah, that's what it, I guess forward or aft. I guess that's another way to say it. So when the center of gravity is forward of the limit, that can make it difficult or impossible to flare on landing. 11 questions left. Why is it important that a pilot lower the speed of his or her aircraft at to or below design maneuvering speed when in rough air conditions? Why is it important that a pilot lower the speed of her aircraft to maneuvering speed when in rough air conditions? It will allow the aircraft to stall before the load limits are exceeded. All right, bring up the figure. What does point A represent on the graph? That's a maximum of lift over drag. So the graph in figure 1 shows typical drag equations for parasite drag, induced drag, and the combination of the two. At point A, we have the minimum total drag, and it occurs at LD max. So maximum lift over drag max. Any increase or decrease in airspeed from point A results in an increase in total drag. So total drag will go up, at or below that, or above it. Neither induced drag nor parasite drag are at a minimum at point A, because increasing airspeed from point A will increase induced drag. Oh, hold on. Neither induced drag nor parasite drag are at a minimum at point A, because increasing airspeed from point A will decrease induced drag, so induced drag will decrease, and decreasing airspeed from point A will decrease parasite drag. So it is the maximum lift over drag. So total drag is at a minimum. Note that the maximum lift-drag ratio occurs at one specific CL, coefficient of lift, and angle of attack. If the aircraft is operated in steady flight at the maximum lift-drag ratio, the total drag is at a minimum. Let me mark that next. A stall can occur at any pitch, attitude, and airspeed. That's true. The angle of attack that provides the most lift for the least amount of drag is approximately 6 degrees. The angle of attack that provides the most lift drag max, for the least amount of drag is probably 6 degrees. So I think you just go up here. The coefficient of lift curve, CL, reaches maximum for this particular wing section at 20 degrees, so that's pretty much the stall speed, and then rapidly decreases. A 20-degree angle of attack is therefore the critical angle of attack. The coefficient of drag curve, orange, which is I think this one, increases very rapidly from 14 degrees angle of attack and completely overcomes the lift curve. At 21. The lift drag ratio green reaches its maximum at 6 degrees, meaning that at this angle, the most lift is obtained for the least amount of drag. Okay, just focus on this curve right here. If an airplane is flown in a trim condition and a momentary pitch change is made via the yoke, so the airplane is flown in a trim condition and a momentary pitch change is made via the yoke, the airplane remains in the new attitude when pressure is released. The airplane displays neutral static stability. So if an airplane is flown trimmed and a momentary pitch change is made with the yoke, the airplane remains in the new attitude when pressure is released. The airplane displays a neutral static stability. It's the initial tendency of the aircraft to remain in a new condition after its equilibrium has been disturbed. If it was a positive, the tendency of the aircraft would go back to its original state of equilibrium. And if it was negative, it would continue away from the original state. So because this one says that the airplane remains in the new attitude, it says neutral. The use of flaps for landing on an airplane will allow a steeper descent without an increase in airspeed. That's easy. Air traffic control instructs you to slow your airspeed and maintain your last assigned altitude. As airspeed decreases, the angle of attack will need to increase to provide the lift required to maintain altitude due to slower airspeed. Easy. Refer to Figure 2. You are in a descent, turning base to final with power on. So power is on. Gear and flaps down. Power on, gear and flaps down in a 30-degree bank over here. But then move the power back to idle. What will happen to your stalling speed? So you go from power on to power idle, so that's back down here to off. Your stalling speed increases from 50 to 62, so it increases by 12 knots. What change in an airplane longitudinal control is required to maintain altitude while airspeed is being increased? What change in airplane longitudinal control is required to maintain altitude while airspeed is being increased? So you have to push forward on the yoke to decrease the angle of attack to compensate for the increase in lift. That makes sense. Figure 4. Back to this one. If an aircraft's static load is 3,000 pounds, what would the dynamic load be in a level 60-degree bank turn? So that would be double, but you just go here, load factor, angle of degree is 60, you go up, the load factor would be by 2, so you take 3,000 pounds times 2 load factor, 6,000 pounds. When will indicated airspeed and calibrated airspeed be equal? And that's at cruise and higher airspeeds. We already went over that. You're going to an airport that has a higher density altitude than your departure airport. When you get to the airport, you can expect your aircraft performance to decrease. That is true because it's less dense air.